Greetings, dear students of the third year. Today I'm going to explain about a very important topic in digital communication, which is quadrature phase shift keying, or simply QPSK. QPSK is a very important modulation technique that is used in many applications. And let's take a look at the applications that use QPSK. First thing is satellite communication. And in this specific scenario, QPSK is used to modulate the signals that are transmitted by satellites to ground base stations or TV receivers. The second application is video extensions, and specifically the MPEG-2 video extension, which applies QPSK modulation in order to modulate the video information. The third application is the Wi-Fi transmission. So our Wi-Fi routers use QPSK in order to modulate the information that is transmitted and received by the Wi-Fi receivers and transmitters. And there are many other communication systems that also use QPSK. So QPSK is a very important modulation technique, and we have to understand it well in order to even understand the other modulation techniques that are used in the communication systems. And regarding the prerequisites that the students should know in order to understand this lecture, so the students should have studied fundamentals of analog carriers and modulation. They should have studied probabilities and random signal analysis, and they should know about complex analysis and integrals. And within the same module, they should have studied binary phase shift keying, which is the main building block of quadrature phase shift keying. So what is QPSK? QPSK is a form of digital modulation that can convey 2 bits per transmission. So instead of conveying only 1 bit in BPSK, the QPSK is able to transmit the double amount of information, which is 2 bits per transmission. And in this specific modulation technique, QPSK, the information is contained inside the phase of the carrier. So let's take a look on how QPSK looks like in reality. First, let's start by the waveform. The waveform of QPSK consists of a cosine wave with a fixed frequency Fc or F carrier, and a variable phase that varies according to the transmitted bits. For instance, if we are transmitting 1-1, this corresponds to a phase of 45 degrees or pi over 4. If we insert here m equal 1, this gives us a phase of pi over 4, which corresponds to this point, and so on. Analyzing this cosine expression, we can write it as in the form of 2 cosines multiplied by each other and 2 sines multiplied by each other. And this expression corresponds to a fixed carrier multiplied by a variable amount and another fixed carrier, sine carrier, multiplied by a variable amount. And these 2 values are given by positive or negative 1 over root 2. And then come these 2 carriers. And in order to transmit this carrier with a higher power rather than unity power, we can multiply by this value, where E corresponds to the energy per bit and T is the duration of the carrier. So what is a constellation? Constellation is a graphical representation of digital modulation carriers. And it corresponds to the starting phase and amplitude of each signal. For instance, if we need to transmit 1-1, this has a starting phase of 45 degrees and amplitude of 1. And in this case, we can map it on the x-axis to 1 over root 2 and on the y-axis to 1 over root 2. A convention that makes it easier to analyze and manipulate these digital modulation constellation signals is to write it in the form of complex numbers. For instance, this point corresponds to 1 over root 2 plus 1 over root 2i. This point corresponds to minus 1 over root 2 plus 1 over root 2i. So it depends whether you are on the upper side, the lower side of the y-axis, or the right or the left side of the x-axis. Another form of QPSK is to have the constellation points shifted by 45 degrees. So it starts at 0, 90, 180, and 270 degrees. And it gives exactly the same results and everything. But this is the most common way to apply QPSK. So let's zoom in to the screen in order to show an example. And here is an example for the constellation that we have shown in the previous slide, where every 2 bits are mapped to a specific phase. For instance, 1, 1 is mapped to a cosine wave that starts at a phase of 45 degrees. 1, 0 is mapped to a phase of 135 degrees. 0, 0 is mapped to 225 degrees. And finally, 0, 1 is mapped to a phase of 315 degrees, or simply 7 pi over 4 radians. And let's assume that we have this stream of bits, 6 bits, that we need to transmit using QPSK. And we divide them into 3 groups. Each group comprises 2 bits, and we transmit these 2 bits using one of these constellations, where every constellation corresponds to a cosine carrier with a duration of 2 seconds. The first 2 bits, 0, 0, and this corresponds to a starting phase of 225 degrees, or 5 pi over 4. Then this is mapped to a carrier cosine wave that starts with a phase of 225 degrees and continues for the next 2 seconds like this, and stops here after 2 seconds. The second group of bits is 1, 1, and this corresponds to a phase of 45 degrees. And there we have a cosine wave that starts at a phase of pi over 4, or 45 degrees, and continues for the next 2 seconds until the second number 4. Finally, we have the last group of bits, which is 0, 1, which corresponds to 315 degrees, and this corresponds to a cosine wave that starts at a phase of 315 degrees, or 7 pi over 4, and continues for the next 2 seconds until the second number 6. The QPSK modulator consists of a serial to parallel module which divides every 2 bits into an I bit and a Q bit. Then comes a polar non-return to 0 converter which maps the 0 bit to -1 and the 1 bit to +1. Then the output of this converter is introduced to a multiplier that multiplies this output with a carrier. For the I bit, the carrier is a cosine wave, and for the Q bit, the carrier is a negative sine wave, as we have seen 2 slides ago. Then the carriers are added together to produce the QPSK signal. So the receiver of the QPSK is the opposite of the transmitter. It starts by a multiplier which multiplies by a cosine wave and a negative sine wave, or the carriers as we did in the transmitter. And then comes an integrator which integrates the value that comes out of here, and the result is introduced to a threshold detector. If the result is higher than 0, then the decided bit is 1. If the result is lower than 0, then the decided bit is 0. And then finally comes the parallel to serial multiplexer, which streams the received bits together. So let's take a look at the mathematical analysis for the error of QPSK. As we have seen that the QPSK transmits 2 bits per transmission instead of 1 bit in the case of BPSK, and this corresponds actually to 2 coherent binary phase shift keying using 2 orthogonal carriers, cosine and sine. The error of 1 bit transmission in binary phase shift keying is given by this function, which is half complementary error function of square root of e over 2n, and the complementary error function is given by this integral. And here e over 2 is the energy per bit, and NO is the noise power, or the noise power spectral density. Then the probability of correct reception is 1 minus this value, because this is the value of error. Then the correct reception probability is 1 minus this value. And in order to get the probability of receiving 2 bits correctly, we take this value and get the square of it. So 1 minus the complementary error function all squared. Analyzing further, we have 1 minus the complementary error function plus 1 over 4 complementary error function squared. So we have this value squared here and this value squared here, and then this 2 times this, which is the intermediate expression. So this is the value of the correct reception probability. If we need to obtain the value of the error probability, then it is simply 1 minus the correct reception probability. And 1 minus this value gives us this expression. If the energy per bit is higher than the noise value, too much higher than the noise value, which is typical for a transmission, then this value is too small, and we can say that the error probability approximately equals this value. So the bit error rate corresponds to the percentage of bits that have been received incorrectly. And this percentage is normalized to 1. And what is the difference between bit error rate and probability of error? They're actually the same thing. However, bit error rate has been used more in a practical context. So it's a more empirical concept. And the bit error rate is simply the number of errors or the bits that are received incorrectly over the total number of transmitted bits. Saying this, if we assume that there is a gray coding as we have shown in the previous slides, we have here this represents 1 1 and this represents 1 0 and 0 0 and 0 1. It is more likely that an error, if we transmit this point, an error would flip it to this point or this point. It is less likely that the noise will move the point all this way, far away. Okay? So here the error is typically, the bit error rate is typically the same as the symbol error rate, because it is more likely if there is an error in one symbol, then there will be an error in only 1 bit. This is the importance of gray coding, that it is less likely that we have 2 bits in error together. And let's take a look at the behavior of the bit error rate versus the SNR for QPSK. As we can see that the curve is going down as we increase the SNR, and this is straightforward to understand, because of course as the signal power becomes stronger than the noise, then there is a less probability of obtaining an error. For instance, if we go for the bit error rate of 10 power negative 4 point, this means that there is only one erroneous bit every 10,000 bits. And if we go through the curve, this occurs when the SNR is 8 dB. So it means that if we transmit the signal with an SNR of 8 dB, we will have only one error every 10,000 bits. And here is a bonus question that I'm asking the students to answer using Kahoot. So you can use your phone in order to access this link, and you will have this question, and it will show whether you understood the concept of constellations or not. Because as we have seen that the QPSK, we have 4 points constellation, and we can transmit 2 bits using these 4 points. So how many bits we can transmit using this constellation? If you know the answer, you can go to Kahoot and ping it. So, dear students, we have come to the end of the lectures. I would like to thank you very much for listening. And if you have any questions or simply anything that you would like to discuss with respect to the topic, please feel free to drop me an email. Bye.